Hello and welcome to this JuliaCon 2022 talk on PointSpreadFunctions.jl, a toolbox for simulating optical point spread functions. So in this talk, I'm going to show you how to use the toolbox, and I will also give you some insights of how this toolbox really does calculate a point spread function. Of course, to use the toolbox, you start by importing it by saying using point spread functions, and then you have to define a number of parameters. And so this point spread function calculation toolbox contains a lot of parameters. Many of them have default values, but a few of them you have to set explicitly. So we're dealing with optical point spread functions here. And what you see here, the most important parameters are, for example, the emission wavelength that you want to simulate, the numerical aperture of your objective, the refractive index of the immersion medium, that would be 1 in air, or otherwise here, I assumed oil, 1.52. And the polarization here is given as an optional parameter. And there are many more optional parameters, as you will see down below. And then two more essential parameters are the size of the data set you want to simulate and the sampling. I would recommend that you use for sampling, you're using the micrometer as a unit. But essentially, it only matters that these units are the same as the emission wavelength. So if you specify this in micrometer, you have to go for micrometers as well here. So what you see is that all this information is then stored in this PSF param structure. Here it's called PP. Then to simulate a point spread function, you have to provide this parameter structure, PP, and also these other two things, sampling and the size information. If you don't provide the sampling, it will use a default sampling that would amount to the upper limit of sampling, so that you're just about sampling it right. Once we've simulated a point spread function, we can display the data, and to this aim, I have actually programmed a little display function that simply puts the XZ central section next to the, on the right-hand side, next to the XY central section that you see on the left. And so this will be for all the following functions as well, and there will be some more complicated displays, as you will see. Good, so now let's think a little bit of what it means to calculate a point spread function. What I show you here is some of the internal workings. So we start with the pupil. So point spread function is defined by the pupil, which is essentially the other side of the objective. And if we are thinking about an illumination point spread function, that's the easiest way to think about it, then this pupil would have a circular sort of aperture here, which defines the numerical aperture, defines in this case the radius of this aperture. And what you see also here is that there's two pupils. One is the X polarization and one is the Y polarization. In this particular case, as you saw before, we have specified an X only linear polarization. That's why there is no Y polarization here. So it's 1 within the pupil and 0 outside, and of course 0 for the Y polarization here. So what we now have to think about is how to get from there to a 3-dimensional point spread function. And for this, two things are essential, and I'm going to switch quickly to a PowerPoint slide to show you what this means. So essentially, the pupil corresponds to this plane here, and the plane, in that pupil plane, you have this circular aperture, and now I show you sort of a side view of this. So this would be the optical axis going to the right. And what happens then is that an electric field that is, for example, polarized here in the Y direction, when it hits a place that is called the Gaussian reference sphere, since we are simulating what is called an aplanatic system, then this ray has to bend and go towards the focus here. And this bending of the ray results in a change of the polarization vector here, which always has to be a transversal wave, i.e. being perpendicular to the direction of propagation. And so this means that we have to sort of flip that vector around here, and this is taken care of in the pupil. So this is handled by basically replacing the two-dimensional pupil that had two components, EX and EY, now with a pupil that's still two-dimensional, but it has three components, EX, EY, and EZ. And these modifications of the pupil will be taken care of. And this is what you see here. And what you can see now is here the X polarization, after it has undergone these effects, and the Y polarization and Z polarization. So interestingly, you see that we don't only get Z polarization as you would expect, for example, for a point here, but for these diagonal points, you also get, because of the three-dimensional nature of this Gaussian reference here and the pupil and the projection on it, you get also this Y component. And in addition, there's another effect that we will go into now, which is called the aplanatic factor. So this essentially means that when we project onto this pupil, so I can go back to this graph that you've just seen here, then we also have an effect, which is a geometrical effect. So that basically means that the size of an area there will change, and this is accounted for in what is called the aplanatic factor. So this aplanatic factor varies whether you're in excitation or emission for fluorescence, and therefore it has to be defined. And by default, it's always assumed that the settings are for emission. But if you want to change it, as you see here, we can specify an illumination aplanatic factor along with the illumination wavelength that might be different. And if we run this, so you now see point spread functions, or rather in this case, the pupils for the different aplanatic factors. So on the top, you see the emission aplanatic factor, where you see that the high angles next to the edge of the pupils are enhanced, whereas the excitation aplanatic factor is different, and it actually is reduced. So it comes down to a division by a square root of cos theta, or a multiplication with the square root of cos theta for these two cases. Right, once we have these three pupils, we now need to propagate them. And this essentially means that in Fourier space, we have to map the pupil onto what is called the reference, what is called the McCutcheon pupil. So that's one way of explaining it. Or you can say you have to propagate the pupil by applying a phase modification to this two-dimensional pupil in every step when we go to different plane. And since we do this for the electric fields, we have to apply this propagation individually for the EX, EY, and the Z field. And what you can see here now is the propagated field already. And for this, we use this function called A PSFs. So A stands for amplitude point spread function. So it gives you the complex valued EX, EY, EZ component of the electric field in a 3D volume. And that is what is shown here. In this particular case, it now calculates this point spread function, and what it displays is the EX, EY, Z here in focus, in the plane of focus, and here it's in an exact section. And the method of propagation that was used here was defined earlier. You can see what it's used. It uses a method that's just called method propagate. So that's the simplest thing. It's using the angle spectrum of plane wave method, and that has a particular problem, as you might see here. Once you get enough out of focus, you get into aliasing problems, and this essentially means that the far out of focus regions suffer from quite severe artifacts. As you see here, these fringes are not supposed to be there. And to avoid that, there's other methods, as I will describe below, but the point is we have here now the amplitudes, and the next step to get to our intensity point spread function is, of course, that we need to come from amplitude to intensity. So what you can do, since the amplitudes are stacked along dimension 4, you can do that by hand if you want. You can simply take the absolute square of this complex valued amplitudes in EX, EY, and Z, and then you can sum them over the fourth dimension. And if you do that, you get an intensity point spread function. But of course, the simple way is you just don't use the function APSF, but rather the function PSF, which then does everything for you. So what you see is that we have now an intensity point spread function, and you see that it's not perfectly symmetric, which is because we assumed X polarized excitation or X polarized emission in this case. But you see that these artifacts are still there because that was simulated with this angular spectrum of plane wave method that has particular problems. So instead of actually going for this type of intensity, which you can think of being like a fluorophore that has the same probability of exacting light from all directions, you can actually also calculate the excitation probability of a dipole. So if you want to do that, you give this PSF parameter structure, this additional argument called transition dipole, and you can specify the direction of that dipole, and then it will calculate a point spread function for you that uses this dipole. As you see here now, we use the intensity point spread function directly to calculate PSF with the size parameter and the various structure, and then you can see here the result. So if we do that, it calculates for us a three-dimensional intensity point spread function with a transition dipole once oriented along the x direction, so that will be shown first here, and here oriented along the z direction. And as you notice, when the dipole is oriented along the z direction, we are particularly only sensitive to the Ez field, and therefore we have this sort of ring-like point spread function as it is seen here, or the zero at the focus in this particular case. So the question is really, how can you now do these various modes of propagation, or actually of calculation of the point spread function? And this is what is done here. And so while it calculates all these various modes, you see you can give method and then different methods propagate you've already seen. Richards-Wolff is a very famous method from a paper by Richards and Emil Wolff. And then there's another method that's called propagate iterative, which is very closely related to the angular spectrum of plane wave method, except that in every single step, it makes sure that these waves that are in danger of causing unwanted interferences are somewhat deleted. So there's essentially something like perfectly matching boundary conditions at the site in every iteration step. It's a little bit slower than the original method, but not dramatically, but it avoids these artifacts, as you will see. Then there's a method called shell propagation, and SyncR is also a very interesting method that is based on the idea that a three-dimensional surface of a sphere, which is the McCutcheon pupil, can be represented in real space by a sync function of the radius. And so it uses this sort of identity and therefore starts in real space and has not this wraparound problem, but it's relatively slow because you need a certain amount of oversampling for it. So what you see here are now these results. We start with propagate, then it comes to Richards and Wolff, and the iterative method shell and SyncR, and you see that the first one has these problems, as you can see here, whereas all the others look essentially identical, and they only differ in speed and of course in the details. So in the percent area, they have small differences, but other than that, they all yield identical results. And so once we've learned how to calculate these point spread functions, we can now think about different modes of microscopy. And so here it gets interesting for practical purposes, and also already quite a variety of different modes have been implemented. So you see here an example of the mode wide field microscopy, which is the standard mode that it calculates by default. But there's also other modes, for example, here the confocal mode, or the image scanning microscopy, which calculates not only one point spread function, but a whole array of point spread function, the two-photon mode of microscopy, or the 4-pi microscopy mode, where you have all possibilities of changing relative phases and stuff like this as well, if you want to do that. In this case of these more complicated modes, sometimes you need not just one parameter structure, but you essentially need to define one parameter structure for excitation and one for emission, and then it gets you the right result by combining them correctly. And here you see, so I calculated this with a slightly smaller field so that it is faster. And here you see the results of these various microscopy modes. You see, for example, the confocal modes then have this optical sectioning, as does the two-photon mode. Here we have an ISM mode, which is image scanning microscopy of a particular offset pixel. So I've just displayed, as you see here, one of this array of point spread functions that you get as a result. So the third one is just a laterally translated mode, which you might appreciate that this point here doesn't sit on the center here, but it's just slightly offset. And here you have the 4-pi microscopy mode. In this particular case, you can see that we are defining a 4-pi excitation and emission point spread function. So we have essentially 4-pi type C as far as I can see here, with polarized detection, which doesn't necessarily need to be the case. Right. Then now we can, of course, take all these modes and make a three-dimensional Fourier transform of each of them. So this is what is done here, and display them. And what we get are the optical transfer function. And you see now again that we have a cut xy direction and xz direction, or here you would say rather kxky direction and kxkz direction. And you can nicely appreciate the shape of the support of the three-dimensional optical transfer function for a fluorescence wide field microscope, as well as for confocal microscope here. The ISM is interesting because it does have the same support here, but it has these funny zeros in between for this off-center pixel. And the two-photon microscopy here and 4π has this typical shape of a 4π point spread function, or rather optical transfer function here. So by default, the calculation type of all of this, as you can see here, is float 32, but you can specify in the parameter structure also D type, so the destination type, which you can do float 64, for example. The one interesting feature as well is that you can specify aberrations. And for this, I'm using the Zernike toolbox. And by using these Zernike modes, you can specify which ones you have, and they're given names here. So you can say Zernike spherical, meaning spherical aberration with a certain coefficient 0.2. And we can calculate the point spread function simply by putting this aberration structure as a parameter to the PSF parameter structure. And you can do, of course, also combinations of them by simply listing them in this list together. So here you see an example of spherical and oblique astigmatism. And to show you better the oblique astigmatism in the display, I'm just showing you out of focus slices in the XZ section here. So you see the spherical aberration has a certain out of focus performance here, as does the oblique astigmatism. It gives you this diagonal astigmatism here. And if we, for example, go instead of +8, I say offset -8, and I display the same thing again, you will see that this aberration has looks like changed a little bit, because now when we go out of focus a little bit differently, here you see this ringing pattern is quite differently here, and the astigmatism has sort of flipped over to the other side because we are out of focus on the other direction. So as for the implementation detail, when we come to Julia, you can see that there was the advantage of using this method argument that was making use of the dispatch mechanisms of Julia. So that's very useful for programming that, because every point spread function calculation routine has actually its own routine, but it automatically branches into that routine via this methods argument, being with one global routine dispatched onto these individual routines like you see here. So you see that there's a routine PSF mode confocal, and if you are not giving that argument, it goes to the general routine, but then calls it with this method argument, which then automatically branches into the correct thing. So if you want to call it by hand, you would need to do it like this, PSF, and then mode confocal and give it the arguments. But I recommend to just use the standard PSF method and use the method argument instead. And yes, as I said, the Zernike polynomials.jl was a very helpful toolbox, and I'm just using the calculation abilities of that toolbox to provide the Zernike polynomials for the modified phase functions of the aperture. And of course, the further advantages of Julia are the high calculation speed, which is really important here, and the dispatch mechanism, as well as the non-existing squeeze functions. So in Julia, there is no squeeze or no automatic squeeze, which is really very good, because then you know precisely what dimensionality your data set has. And if you go to other languages that automatically start to squeeze your results, then you get into lots of trouble there, which doesn't happen in Julia. And if you want to squeeze, of course, you can do it by hand. Here's an example to just show you how these various parameters were structured. So there's an abstract type PSF mode from which all of these other types derive. And so there's these various modes are all sort of inherited from PSF mode, as well as all the methods are inherited from PSF method. And this way they are defined, and then you can make sure that the user really provides a correct parameter here. So there's two interesting points that I want to show you. now, which is the first one I call the zoom trick. And so what I do here is that to speed up this whole calculation, you can think about what sampling is actually required from the individual steps. And to calculate a point spread function, as you've learned above, you need to first calculate an amplitude pattern. In the general case, a EX, EY, and EZ based vectorial amplitude patterns. And then you need to calculate the intensity from it. But the amplitude patterns can be sampled at a coarser grid than actually the final point spread function, because that step of absolute square at the very end, that basically doubles your sampling requirements in X, Y, and Z. And that means that you're losing sort of a factor 8 in speed. And it turns out that it's quicker to resample your data at this step than to originally calculate with the sampling. So that is done by default, but you can also specify that you want to really do all the calculations on the same grid. So what you see here is a comparison. Well, you see here just a demonstration of this whole thing. So if I'm looking at a three-dimensional Fourier transform of the amplitude pattern, you see here that this is part of this McCutcheon pupil. So it's actually just a stretched version for you to see it nicer. So I've used different samplings in X and Y and Z. You see that's part of a shell. Yeah, so a shell, a three-dimensional shell cut in XY, in XZ. And you see that this is just about sampled, right? And if you then go to the intensity by taking the absolute square in real space, you'll get an autocorrelation in Fourier space, which then doubles the support region in X, Y, and Z, and that means you have to sample it correctly. And when you go from here then to a confocal microscope, as in this case simulated here, then the confocal microscope needs again a factor of 2 higher sampling, because it leads to essentially a convolution of one of these functions with another one that looks very similar. And so that means starting from a confocal, you can actually downsample a lot. You can sample the amplitude on a little grid that contains this bit. Then you go here, that's twice as big, and then you go again twice as big. And that speeds up the whole calculation enormously. And here's a comparison where I'm just comparing the standard calculation as shown on top with the one that has this use resampling folds feature, which basically then does not resample and just calculates everything on the same grid. And you see that the speed up is quite big, and the results are virtually identical because this upsampling doesn't add to it. So you see that if we use the upsampling trick, the automatic upsampling trick, we get the result in 2.4 seconds, or 2.5 seconds, and 12.4 seconds is what it takes if you really resample everything, or don't resample, you just sample everything on the same grid. And so this is partly due because of the Fourier transforms toolbox, Fourier tools toolbox that has a very fast upsampling function in it. And so just to finish off, there's one last little thing, which is this, what I call the Whitefield Z undersampling problem. You see here that we have an aliasing problem when we undersample in Z. It turns out that normally that's not a problem, but when we upsample and expand zeros in Fourier space, there is a problem. What it really does, it just shifts everything to the middle to avoid the problem. And so when you do that, then it works all fine, but it's a little bit of work to program, and it's such that it first shifts it to the middle, then expands the zeros, and then it can actually put it back where it's supposed to be. So that's sort of a trick for coarse set sampling that also makes it faster. So with that, I'm at the end, and I just want to finish off by saying there's of course many things that still need to be done. So using unifold packages would be one thing. There can be the implementation of aberrations in the richest involved method that doesn't support it currently, and then making a CUDA compatible or allowing Zygote to differentiate through the toolbox would be really. I want to end by thanking foremost Dina Ratziman-Drazy, who worked with me on point spread function calculations and did all her programming in MATLAB, but that was very helpful. And Felix Wechsler, who gave me lots of help in Julia programming, and Martin Kielhorn, who came up with this sync-R method that there's this relationship between the Fourier transform. So I thank you very much for listening, and I hope you enjoyed the talk.